Hi and welcome to Module 4.2. In this module we will talk about a discrete Fourier transform in more detail. We will introduce it formally, we will show some examples, and we will show you how to interpret a DFT plot. So in the previous module we introduced the Fourier basis for Cn. We showed that it has a dual nature. You can interpret it as a family of signals, finite length signals of length n. This family is indexed by an index k, and each element of each signal is given by e to the j 2 pi over big N times nk. And both n and k will move from 0 to big N minus 1. Another way to look at this family of signals is to write them up in vector notation, in which case you will have a family of vectors indexed by k, and each element of the vector will be again e to the j 2 pi over n times nk. So once again, it's a complete isomorphism between the signal notation and the vector notation. We showed that the vectors, these n vectors, are orthogonal, and therefore they constitute a basis for Cn. They're not orthonormal, and therefore we will have to normalize the inner products explicitly. Okay, so we're in Cn, and given an arbitrary element of Cn, call it x, we want to express x in this new Fourier basis. Well, so we know that the analysis formula will give us n new coefficients for the vector in the new basis, and each coefficient, which we call big X of k, will be simply the inner product of x with each vector of the new basis. If we want to go back to the original representation for x, we simply have to sum a scaled version of all the basis functions, and the scaling factor is none else than the coefficient that we found in analysis formula. Please note here that since the basis is not orthonormal, we will have to normalize somewhere, and we choose to normalize in the synthesis formula by dividing the sum by big N. Well, so this is the Fourier transform really. Think about it. We usually assume that the signal x lives in the time domain. In vector notation, that means that we can express x as the sum of each component of the vector, x of k, times the kth canonical vector, ek. And ek is nothing but a delta in n minus k. So each canonical vector does nothing but extract one precise time instant. Here we're saying that we can express the same vector x as a linear combination not of delta functions, but of sinusoidal functions. What will change are the coefficients of this expansion, and these coefficients are given to us by the analysis formula. So we're moving from the time domain to the frequency domain. To stress that this is just a linear algebra operation, we can express the change of basis in matrix notation, as we always can in the case of Euclidean spaces. So if we define big W of n as e to the minus j 2 pi over n, or simply W when big N is evident from the context, then we can write this big matrix where we put basically the conjugate of each basis vector in each row. And with this notation, the analysis formula will give us a vector of Fourier coefficients as the product of the matrix W times the signal vector x. Vice versa, the synthesis formula will allow us to retrieve the original vector in the canonical basis simply by applying the Hermitian operator to the matrix W. And I remind you that the Hermitian operator is a combination of transposition and conjugation of each element of the matrix. So we multiply the Fourier coefficient vector by this matrix and normalize by 1 over n, and we get back the original vector. A third way of looking at the discrete Fourier transform is to consider explicitly the operations involved in the transformation. In this case, we will consider signals explicitly, and this is a notation that is particularly useful if we want to consider the algorithmic nature of the transform. So here we will consider that the frequency domain signal that we obtain after the transformation is obtained as the sum for small n that goes from 0 to big N minus 1 of each element of the signal vector times e to the minus j 2 pi over big N times nk. So what we're performing here is the inner product in an explicit fashion. We move from an n-point signal in the time domain to an n-point signal in the frequency domain. The synthesis formula is the dual of that, with the only difference that here we have to remember to put the normalization coefficient in front. And so from an endpoint signal in the frequency domain, we go back to an endpoint signal in the time domain. Maybe this is a good point to remind you that although we talk about time domain, in the discrete time world, time is really adimensional. So it won't be time in the sense of seconds or any other physical unit of measure. It will be just an index that moves over the range of integers. So let's look at some examples. And one property that we will use in the following, which is obvious from the definition of inner product, is that the DFT, the discrete Fourier transform, is a linear operator. So if you have the DFT of the sum of two vectors, this will be equal to the sum of the DFTs, and the same goes if you have a scalar multiplication. So the first example is the DFT of the discrete time delta. You can see the delta here in the time domain. It is 1 and 0 everywhere else over the support of the signal. Now if you work out the inner product of the discrete time delta with the Fourier basis vector, you will see that the delta will isolate the 0th component of each basis vector. So the product will be 1 for all values of the index k. And so the Fourier transform of the discrete time delta is the constant 1. In other words, the delta contains all frequencies over the possible range of frequencies. The dual example of that is the Fourier transform of the unit function. So you have 1 for all values of the time index, and if you work out the inner product, you will see that the Fourier transform corresponds to a delta. This is quite intuitive because this is nothing else than the orthogonality formula that we showed before, so it will be equal to big N in 0 and 0 everywhere else. Okay, so now let's try to compute the DFT of a sinusoidal function. We take x of n to be 3 times the cosine of 2 pi over 16 times n. We are in C64, so n, the dimension of our space, is 64. And the fundamental frequency of our Fourier transform will be omega equal to 2 pi over 64. All frequencies in the Fourier basis will be a multiple of this. With this in mind, we can start by expressing the frequency of our sinusoid as a multiple of the fundamental frequency for the space. So 2 pi over 16 will be equal to 2 pi over 64 times 4. With this now, we can use Euler's formula that says that cosine of omega is equal to e to the j omega plus e to the minus j omega divided by 2, and express the original cosine as the sum of two complex exponentials, namely e to the j 2 pi over 64 times 4 times n plus e to the minus j 2 pi over 64 times 4 times n. Now we don't like this minus here, so what we're going to do is exploit the fact that we can always add an integer multiple of 2 pi to the exponent of a complex exponential, and the point will not change on the complex plane. So minus j 2 pi over 64 times 4 times n plus j 2 pi n will be equal to e to the j 2 pi over 64 times 60 times n, because n is an integer. And so now we have expressed the original signal as the sum of two of the Fourier basis vectors. So x of n will be equal to 3 over 2 times basis vector number 4 plus basis vector number 60. At this point, we can apply the DFT as an inner product with each vector in the basis, and we can exploit the linearity of the operator. So xk, the kth Fourier coefficient, will be equal to the inner product between basis vector number k and our signal. If we replace the signal with what we just computed before, we have this formula here. Because of linearity, we can split this into two distinct inner products, and we have 3 over 2 times the inner product of the generic basis vector times basis vector number 4, plus 3 over 2 times the inner product of the generic basis vector with basis vector number 60. But now we know that this guy here will be non-zero only for k equal to 4, and this guy here will be non-zero only for k equal to 60. When k is equal to 4, this will be equal to big N, namely 64, and when k is equal to 60, this will be equal to, again, to 64. And so if we work out the arithmetic, we get that the DFT of our original signal is equal to 96 if k is equal to 4 or is equal to 60, and 0 otherwise. So we can plot the DFT of our cosine, and it will be 0 everywhere in the real part except in 4 and in 60, whereas the imaginary part will be 0 everywhere. Okay, so let's try another example. Here we take the same cosine as before, but we add an initial phase. So we take 3 times the cosine of 2 pi over 16 times n plus pi over 3. The first thing we do is to express the frequency of the cosine as a multiple of the fundamental frequency for the space. We're still in C64. Then we use Euler's formula and we decompose the cosine as the sum of 2 conjugate complex exponentials. And we can express the phase term, we can take it out of the complex exponential as a complex scalar multiplicative factor. So then we can use the same trick as before to bring this negative frequency into the 0-63 range, and we obtain that our signal is simply 3 over 2 times the sum of basis vector number 4 multiplied by e to the j pi over 3 plus basis vector number 60 multiplied by e to the minus j pi over 3. And when we compute the DFT, we take the inner product of that with the generic basis vector for the Fourier basis, and just like before, we obtain just 2 non-zero values. When k is equal to 4, the first term will survive, giving us a DFT value of 96 times e to the j pi over 3, and when k is equal to 60, we will get 96 e to the minus j pi over 3, and 0 everywhere else. We can plot the Fourier transform like before, and we will have in this case non-zero values both in the real and in the imaginary part. Probably a clearer way of plotting this Fourier transform, however, is to plot both the magnitude and the phase of the Fourier coefficients. If you remember what we just computed, the magnitude will be equal to 96, both for k equal to 4 and for k equal to 60. And the phase will be equal to pi over 3 for k equal to 4 and minus pi over 3 for k equal to 60. This way of plotting the data shows us that we can use the Fourier transform to separate the amplitude of a sinusoid from its phase. So I'm sure that by now most of you will be saying, okay, but what about sinusoids whose frequency is not a multiple of the fundamental frequency for the space? What do we do there? And indeed, let's say we take a sinusoid with frequency 2 pi over 10, so 3 times the cosine of 2 pi over 10n. Well, this cannot be reduced to a multiple of 2 pi over 64. It is a frequency that actually falls between 2 pi over 64 times 6 and 2 pi over 64 times 7. So what do we do there? Well, we simply compute the DFT numerically. Remember, the DFT is an algorithm that requires a finite number of operations and that can be computed with the desired level of precision in numerical packages such as MATLAB, or you can even write your own C code routine to do so. We will see later in Module 4.9 that very, very efficient algorithms exist to compute the DFT. So this is not a problem. So we run the DFT in a numerical package and we obtain the magnitude and the phase. Now if you see, a high level of magnitude indicates a similarity of the input with the corresponding basis vector. It's a definition of inner product. So here, unsurprisingly, the input is particularly close to basis vectors number 6 and number 7, as we showed before, and by extension to 64 minus 6 and 64 minus 7. But in order to obtain the exact 2 pi over 10 frequency, we need contributions from all the DFT coefficients in the 0 to 63 range. And similarly, the phase is non-zero for the whole range as well. This is actually a general result. Unless you have an input that is a linear combination of basis vectors, most of your DFT coefficients will be non-zero. Let's, for instance, consider an example that we can compute exactly. Let's consider the DFT of the step vector in Cn. We're in Cn and we have a signal that is 1 for n equal to 0 to m minus 1, and then is 0 everywhere else. If we compute the DFT, we can just write the inner product explicitly and replace the values for the input signal. So now x of n will be equal to 1 for small n that goes from 0 to big M minus 1, and 0 everywhere else. So this simply reduces the sum that originally went from 0 to big N minus 1 to 0 to big M minus 1, and the coefficient for each term will be 1. So this is a geometric sum. We have seen that before, right? So sum for n that goes from 0 to big M minus 1 of a to the power of n is equal to 1 minus a to the power of big N divided by 1 minus a. So we apply that, we obtain this ratio, and now we're going to perform a little trick. So let me write it here on the side. If we have an expression of the form 1 minus e to the minus j alpha, we can always collect half the phase of this complex exponential and write e to the minus j alpha over 2 that multiplies e to the j alpha over 2 minus e to the minus j alpha over 2. Why do we do this? Well, because this guy here is nothing else than 2j sine of alpha over 2. So we can separate this element into a real valued component and into a phase term. So we do this for this expression, and we collect half the phase here and half the phase here, and if we work out the algebra, we get that the DFT coefficients are equal to the ratio of two sine functions time a pure phase term here. Now, I'm not going to read out loud this formula, but we're going to try and plot it, so we're going to try and get some intuition on how this is going to look. So first of all, if we think about the magnitude of this coefficients, note that this phase term will always be equal to 1 in magnitude because it's a pure phase term. So the magnitude will be determined by the ratio of these two trigonometric functions. In 0, this ratio is ill-defined, but if you go back to the expression for the DFT sum, you can see that if you put k equal to 0, it becomes simply the sum of big M ones. So the DFT in 0 is equal to M. Another point to notice is that if k is a multiple of n over m, then the numerator here will be equal to 0, and so the DFT coefficient will be equal to 0. Finally, the phase, which depends only on this complex exponential here, is linear in k, as you can see from the formula, except as sign changes for the real part, where we will have a jump of pi. So if we plot this in magnitude and phase, we have that the shape looks like so. We are using a length 4 step in C64, so n over m will be equal to 16, and indeed the DFT coefficient will be 0 in 16, 32, and 48, and all multiples of 16. The phase is indeed linear in k, and whenever there is a discontinuity in the sign of the real part, we will have a jump of pi. So discontinuity, you can see it here. Here we're plotting the magnitude of the real part, but in reality, if we were to plot the part with a sign, this would become negative here, go back to positive here, and then go negative here. Notice that here the phase extends from 0 to minus 4 pi. This is a little bit unusual. We said that 0 to 2 pi or minus pi to pi is the only interval that we're interested in discrete time because everything maps back to that interval. So it's very common to see plots where the phase is wrapped over the minus pi interval. What that means simply is that for every value of the phase, we add or subtract 2 pi until we fall back into the minus pi interval. So here's the same plot as before, but with the phase wrapped. So now that we've seen some examples, we can give some general guidelines on how to interpret a DFT plot. So first of all, you will have frequency coefficients from 0 to big N minus 1, where n is the size of your vector space. The first n over 2 coefficients correspond to frequencies less than pi. So we're talking about counterclockwise movement of the point on the complex plane. Frequencies from n over 2 to n minus 1 are frequencies that are larger than pi, and we interpret those as clockwise rotations in the plane. Frequencies in this band, close to 0 and close to n minus 1, are low frequencies in the sense that they indicate a slow rotation around the unit circle, either counterclockwise or clockwise here. whereas frequencies centered around n over 2 correspond to the fastest frequencies in the vector space, either clockwise or counterclockwise. So if we go back to the examples that we saw before, if we take x of n, the unit signal, so equal to 1 for all points, well, this is the slowest possible signal in the sense that it never really changes. It remains constant for the whole duration of its life. And correspondingly, its Fourier transform only contains the lowest frequency coefficient. It's not even a frequency in a sense, because k equal to 0 is absence of movement. Conversely, if we take x of n equal to cosine of pi n, which is equivalent to, say, minus 1 to the power of n, which is the fastest signal in discrete time, its DFT will only have one non-zero coefficient exactly at the highest frequency point. Now, if you recall Parseval's theorem from module 3.3, we know that the energy of a signal will not change if we change the underlying basis. So, conservation of energy across domains. Now, the square magnitude of the kth DFT coefficient gives us an indication of the energy associated to the underlying oscillation that composes the signal. So the signal's energy at a given frequency is proportional to the magnitude of the DFT coefficient at that point. If we go back to one of the examples that we worked out before, and we take a sinusoid with a frequency that is a multiple of the fundamental frequency for the space, we see that the magnitude is non-zero only in 2 points, and that indicates that the energy of the signal is concentrated at these 2 frequencies and nowhere else. If we take the DFT of the unit step, on the other hand, we see that although most of the energy is concentrated on the low frequencies, there will be energy all across the spectrum. So we need energy at all frequencies to create a step. Finally, let's try and formalize something that you might have noticed already, and that is the fact that the DFT of real signals is symmetric in magnitude. Now, symmetric here is in quotes because when we're dealing with finite length vectors, symmetry depends on the parity of the vector. So for odd length signals, we have a situation, and for even length signal, we have another situation. In general, what we say is that the magnitude of the kth DFT coefficient will be equal to the magnitude of the coefficient computed in big N minus k. And this is valid for k that goes from 1 to n over 2 in floor. So in the case of odd length signal, what we have is the following. The coefficient in 0 is free. The coefficient in 1 will be equal to the coefficient in big N minus 1. Here we have an n equal to 5, so this will be equal in magnitude to the coefficient in 4. And the coefficient in 2 will be equal in magnitude to the coefficient in 3. Now, if we take n equal to 6, so an even length space, the coefficient in 0 will be free. The 1 in 1 will be equal to the 1 in 5 in magnitude. The 1 in 2 will be equal to the 1 in 4 in magnitude, and the 1 in k equal to 3 will be free. What that means is that for real valued signal, the magnitude of the DFT is completely specified by only the floor of n over 2 plus 1 coefficients. So for n equal to 5, for instance, we only need 3 coefficients, and for n equal to 6, we only need 4 coefficients. The reason why this happens is because when we take the DFT of a real signal, although we end up with complex coefficients, the coefficients will have to combine together to give back a real signal. So coefficient will be complex conjugate across the n over 2 index.